Isothermal process, as we are discussing, this is the indicator diagram and this is it. Indicator diagram. Okay. Here P varies inversely with V at constant temperature. Now we learn to get the slope of the curve. Slope of an isothermal curve. Slope of an isothermal. Slope of an isothermal. In the case, the slope, suppose we are trying to get the slope at any point P, we have to draw a tangent. You have to draw a tangent, and this tangent, as you see, is making an angle acute with the negative side or obtuse with the positive side of volume axis. At this angle theta, we can say this is the slope, and the slope theta or tan theta is equals to minus of dP upon d. Tan theta is minus dP upon d. Now check. We have PV is equals to nRT. If I differentiate both sides, what we get? V dP plus P dV is equals to nR, and dt is 0, so right hand side will be 0. Or we can write down dP V dP is equals to minus of P dV, or minus V dP is equals to P dV, or minus of dP upon dV is equals to P upon V, or we can say dP upon dV is minus P upon V. So slope is dP upon dV, right? And since it is coming to be negative, so we can say what? This is what? Minus of P upon V. This is called the slope of the isotherm. Indicator diagram we have here, and I have drawn a slope. Next term that we have to learn here is isothermal elasticity. That means thermal elasticity of the system in this process. Isothermal elasticity, as you know, the elasticity, the coefficient elasticity, it is called sigma. Sigma is what? dP upon V dV, and sign is minus, or we can write a minus of dV upon V. So sign sigma will be minus of V dP upon d. V dP upon d is that. Let us check what is it then. Again, have the gas equation PV is equals to nRT. We can do the differentiation again. So if I get it from here, or we can say we have already, we have dP upon dV, the slope, as minus of P upon V. So minus of V dP upon dV is equals to P. That means we can say sigma, the elasticity, is equals to the pressure. That is what about isothermal process. And just for reminder purpose, here we can check. We can say that du was 0 in this process. No work is done. That means whatever heat from the first law of thermodynamics, if you write dq, which is the amount of heat transferred to the gas, supplied to the gas, given to the gas, dq is equals to dw only, as du is 0. They may ask you corresponding graphs over here. So no problem. We can check it like this. Suppose they have given you TV graph, and the graph is going like this. Yes, this diagram shows what? That the system is taken from state A to another state B when temperature T is constant. Definitely, this is a graph or TV graph for an isothermal process. This is what? A TV graph for an isothermal process. And here you see this may be V1, this may be V2. Okay. The next process, thermal process is adiabatic process. in which dq is 0, that means heat is neither absorbed nor released. That means realization can be done in this way. If we have a container having piston over here, right, and we have some gas, say n moles of the gas. We have n moles of the gas in this container, and the piston as well as the boundary of the container. Piston as well as boundaries of the container is insulated. If this kind of insulation, that means it is covered by an insulating material like a woolen blanket, etc. So when this kind of things are done, this is insulated. When we are not allowing, that means we are neither not allowing any heat to escape out nor allowing any heat to enter into the system. Such as the arrangement is an adiabatic process, or in other words we can say for adiabatic process what we need that the container must be ideally and insulated. An insulating conductor must be there. Practically, ideal insulator, making an ideal insulator is not possible, right? But anyway, and the second one, the processes are, this process is exactly a fast process, right? That is what one other way of doing an adiabatic process, by making the process fast. Why we are making the process fast? Exactly, the concept behind making the process fast is not to provide any time to the system to exchange heat with the surroundings. That way the process is fast. For example, bursting of a tire. Or another one may be considered to be propagation of sound. All these are the examples of adiabatic processes. In adiabatic process, as we have said, there is no heat allowed to enter. And now, see what happens then. If we can reduce the pressure, we can increase the pressure. That means if we increase the pressure, put the piston down, the gas will compress, but this time adiabatically, right? So let us consider the case like this. Suppose we have an ideal conductor. Once more, check it like this. An adiabatic container is there. Check the things are as usually insulated. Complete insulation is there from the surrounding. Isolation is there, and some gas is there. And say we have a block of mass and displacement, and this is now in the equilibrium position over there. That simply means pressure. If A, suppose as usually A is considered to be area of cross section of piston. We can say what? P is equals to mg upon A, force upon area cross section. This is what pressure over here. Initial pressure 1, we call it P. So pressure is P1. Now if I press it, keep it another block. Now these two blocks are there having total masses 2 mg, and you notice that the gas piston will come down to position number 2. This time there is a compression. So what kind of compression is there? This is water compression. This is an adiabatic compression. Okay. And the relation between pressure and volume, adiabatic relation here is there. New volume is V2. Suppose the new volume is taken V2. Initial volume is V1. Here the relation between pressure and volume is given as, P V to the power gamma is a constant. P V to the power gamma is a constant, where gamma is Poisson's ratio known as Cp upon Cv of the gas. Cp molar specific heat at constant pressure, Cv molar specific heat at constant volume. Pv to the power gamma is constant, or we can write down P1 V1 to the power gamma is equals to P2 into V2 to the power gamma. So for calculation purpose, we must keep it in mind that P1 upon P2 is equals to V2 upon V1 whole to the power gamma. This is what the here we have putting this relation in this equation, putting P in P v to the power gamma constant C. P as N R T upon V into v to the power gamma is a constant C. Take this one, NRT is also a constant. So we can write down what T into v to the power gamma minus 1 is another constant. So this is what the relation between absolute temperature T taken in T and the volume of the gas V, or here we can say T1 into V1 to the power gamma minus 1 is equals to T2 into V2 to the power gamma minus 1. This kind of cases are there. I can replace P also from V from here, replacing V. Suppose we have P equals to nRT, and so V is equals to nRT upon P. And putting this in this equation, P to the power gamma, putting this equation here in place of V, I can write down this as P into nRT upon P whole to the power gamma. So this is what exactly, and this is constant. We can write down P 1 minus gamma into P to the power gamma. This is a constant. This is the relation between the pressure and temperature of the gas in adiabatic process. So we have, finally we can summarize it as three basic relations. One between pressure and the volume, or P to the power gamma, we can say is a constant. The second one we have got it here as this is number 2, T v to the power gamma minus 1, and that is another constant C. And third one, P to the power 1 minus gamma into T to the power gamma is another constant C. These are three relations, 1, 2 and 3, that are frequently used in numerics in solving problems. Now come to the point again. When you are using, say, in this process, now see this process in limelight of the first law. First law says what? As per the first law, dq is equals to du plus dw, right? Because the heat supply to the system is used by the system in two ways. One, for increasing its internal energy, and second, in performing a mechanical work. But here in the adiabatic process, since no heat is allowed to enter the system, we can say dq is equals to 0. dq 0 means du is equals to minus of dw, or vice versa, right? We will write dw as minus du. How will I interpret these two results? We can interpret these results like this: minus dw, work done by the gas, is negative, or we can say this as in linguistic form, we can say it like this, that work done on the gas, will do what? It will do only one thing. It will do what? Work done on the gas will be equals to increasing internal energy of the gas. Whereas in the second case, what happens? dw, when work done is positive, that is work done by the gas. Work done by the gas is equals to work done by the gas as the loss in internal energy of the gas. Since the system is not supplying any heat, so if it is compelled to do some work, what will happen? Definitely it will do at the cost of its internal energy, causing a loss in internal energy of the gas. This lost energy, or this loss in energy, internal energy of the gas, will be equivalent to the work done by the gas. The reverse case, the first one, work done on the gas. If I press the piston down in the example given just before, that if the work is done on the gas, will be do what? This work on the gas, since it is not allowed to escape out of the container, escape out of the system, it will do what? It will increase the internal energy of the gas. That is what the case is. And from there, so we have the formulas now to calculate the internal energy. We all know internal energy is what? Du. And the formula is universally correct. NCVDT. So this is what du is equals to NCVDT. We can use it like that. NCVDT formula. And work done by the gas in additive process. We can do it easily. Work done P is equals to, we know where dW is equals to PdV. PdV is the work done P, and we have PV to the power gamma as a constant. PV to the power gamma is a constant. So dW is equals to PV to the power gamma as a constant. dW is PdV, and P, since it is not a constant, P is what? A constant term. So C, P is equals to C upon V to the power gamma. Right? And that is equals to, in place of P, I can put it over there. Since P is not a constant over here, P is a variable, P is a function of V, P varies this way with V, or we can say P is proportional to V to the power minus gamma. And we can put it over here, in place of P, if I write C upon V to the power gamma into dV upon V, this is the work done W. On integration of both sides, what you get? C as dV upon V to the power gamma. dV upon V to the power gamma. So integration, and say initial volume is V1, final volume is V2. I can write it like this: C into V to the power gamma. You know well the formula. Integration of x to the power n dx is equals to x to the power n plus 1 upon n plus 1 plus c, constant over there. So here it is what? V to the power gamma, that will be C into V to the power gamma plus 1 upon gamma plus 1, and this will be within the limits V1 to. So this is the way. Here we have C and CVDT, another way, and dW. Since we have dW is equals to minus of du, so we can make it equivalent to the loss in potential energy, work done by the gas. So there are ways. In whatever way we can calculate it like this. And see, in adiabatic process, if I plot a graph like this, see, there are two indicator diagrams given. Let us first PV graph is given. There are two graphs plotted over here. One is like this. One is like this. The graph is taken like this. Second one is like this. At this point, at the same point, they are intersecting. At this point, suppose at the point X, they are intersecting each other. Okay. So there are two cases, two indicator diagrams. One is plotted by the black, other by the red color, and we can check the slope of the curves at these 2 points. So plot a slope to the black one. Yes, you will get it like this. To the red one, you get it like this. Okay, since this is theta 1 and say this is theta 2, one can check it. Theta 2 is greater, theta 1 is small. Now, so to get the slope of the PV curve in adiabatic process, we have slope the PV to the power gamma. We have the relation P to the power gamma is a constant C in adiabatic process. PV to the power gamma is constant. PV to the gamma is constant. One can easily do it. So in now differentiating both sides, what we get? P into gamma time into V to the power gamma minus 1 dV plus V to the power gamma V to the power gamma into d, that equals to 0. And slope is, obviously this is PV curve, slope is considered to be dP upon dV. Let us check dP upon dV, find out. So just take it on the other side. We have what? P gamma P V to the power gamma minus 1 dV is equals to what minus of this is equals to v to the power gamma into dv. So dp upon dv, take it dp upon dv as dp upon dv is minus of gamma times of p v to the power gamma minus 1 upon v to the power gamma. So this will be minus of gamma times of, just solving, just by solving it we get it minus gamma into p upon v. So slope is minus gamma p upon v. Okay, if you remember in isothermal process, during the isothermal process or during finding the slope of the PV curve in an isothermal process, what we got? We got dp upon dv as minus of p upon v. dp upon dv is minus of p upon v. But here we get dp upon dv as minus gamma times of p upon v. That means tan theta 2, that indicates tan theta 2, here it is greater, tan theta 2 is greater than tan theta 1. That means dp upon dv is more in case of isothermal adiabatic process. So which one is more? Definitely from these two graphs, say AB and C, two indicator diagrams are there for two different processes. One can easily identify that the red one is showing adiabatic process, is an adiabatic curve, whereas the curve AB is representing an isothermal curve. And the ratio of these two slopes, the ratio of the slope, this is the slope. It means ratio of slope in isothermal to adiabatic to slope in adiabatic curve, adiabatic process to slope in adiabatic to slope in isothermal. Adiabatic slope to isothermal slope. Yes, the ratio is gamma, which is Cp upon Cv. The Poisson's ratio. The things are very simple, but during the numericals we have to keep it at the turn step so that one can use it instantly without losing any time. And similarly, we can go for elasticity. That is thermal elasticity in an adiabatic process. So this is called adiabatic elasticity. What will be the elasticity of the system? Thermal elasticity in case of adiabatic processes. During adiabatic process, obviously sigma in adiabatic, we know that sigma is what? Nothing but minus of v dp upon dv. So dp upon dv is this is that. So v into that, it will be what? Minus of that, and the minus will cancel. It will be gamma times of p. That means sigma in adiabatic upon sigma in isothermal. This is to both the this ratio is also equals to gamma Poisson's ratio, which is Cp upon C. Okay, now the next third type of process which we usually prefer to do, and third one is an isobaric process. Isobaric process is what? In which pressure of the gas is kept constant. Pressure of the gas is kept constant. Okay, say we have a PV curve, right? Its indicator diagram will be obviously whatever changes means Vp is constant, where V and T remains what? V and T remain variables, keeping P constant. So the diagram, the indicator diagram of this process will be definitely this one. And here we get Charles law. This is also the interpretation of Charles law. Charles law says what? For a given amount of the gas, for a given amount of the gas, okay, at a constant pressure, volume is directly proportional to P at constant P. That means the VT graph will be going to a straight line like this. Okay, this is going to be directly proportional at constant P. So this is what volume versus temperature graph in an isobaric process, whereas this is what pressure into volume graph or indicator diagram for an isobaric process. An isobaric process is the process in which the pressure is kept constant. Pressure is kept constant. Okay. So this is the case. Now we may find out the change in internal energy in this process and other things also. Change in internal energy du in an isobaric process. How to realize this case isobaric? Yes, we have a container as usual, right? And the piston is placed over here, somewhere else like this. Okay, and pressure is kept constant. That means the weight is there and it is not allowed to dip. Pressure has been made constant. It means in that process we are going to keep the pressure constant, and in this case work done du is equals to, you know well, NCV dt. Same formula, right? NCV dt is there. We can find out is that like this, Cp upon Cv is equals to gamma. We know. So Cv is equals to Cp and Cp minus Cv is equals to R. Depending upon this, we can divide by this. Cp upon Cv minus 1 is equals to R. Cp upon Cv is R upon Cv is gamma. Gamma minus 1 is equals to R upon Cv, or we can write down Cv as R upon gamma minus 1. Cv is equals to R upon gamma minus 1. We can write down this as Cv as du as what? N into R upon gamma minus 1 into dt. Changing it, integrating it with the limits of temperature, we make it that T1 to T2, that's U1 to U2, or delta U will be nR T2 minus T1, this upon gamma minus 1. That is how we calculate change in internal energy in an isobaric process. And work done. As usually, it is very easy to understand. Pressure is constant, say pressure is kept constant at P, whereas the system is taken from A to B, means from a volume V1 to V. That means without any change in the pressure, the gas is expanding. The gas is expanding at a constant pressure. That means pressure has been kept constant. And I told you earlier also that the benefit of using indicator diagram is to calculate the work done easier. So in that case, we can get the work done W as work done by the gas in this process will be obviously area under the rectangle. Area of the rectangle will be its length into breadth. The length is P into this gap is V2 minus V1. P into V2 minus V1. This can be expressed in the ways also PV2 P into V2 minus V1, or PV2 minus P V2 minus P V1. PV is equals to nRT. We can write down this as PV1. PV1 is equals to nRT1. Similarly, PV2 as nRT2. We can use it like this, PV2 minus this, or it will be nR into T2 minus T1. This is taken from temperature T1 to T2. So this thing can be done also over here in this process. We can find out this way. Temperature initial and final is given. We can't find out the work done from VT diagram. Work done during the gas can be find out only during this from this indicator diagram. This is the another process, thermodynamic process, which we usually do. And next one is fourth one, is isochloric process. Isochloric process means when the gas is kept in a confined container and pistons are also rigid, nothing is allowed to expand or contract. That means if this is the case, the gas is kept in a container, say we have n moles of the gas kept over here, and all the walls of the container are made rigid. That means they are not allowed to change their shape, neither to expand or to contract. That means isochloric process is a process in which volume of the gas is kept constant, volume of the system is kept constant. So this is the process which is performed by keeping volume constant. Now if I supply some heat to the system, say if I supply, you may ask a question, the question may come in your mind. So what will be the use of this heat that the system has absorbed, or whatever the utilization of the heat which the system is given, right? Since the gas is neither going to allow it to expand nor we are allowing it to compress. So that means neither expanded nor compressed, right? So definitely volume is kept constant, or we can say delta V is 0, change in volume is 0, and we know well the work done dW is written as P dV. Since dV is 0, work done by the gas is 0, or work done on the gas, both is 0. So, and the line of this, and by using the law, first law of thermodynamics, which states dq is equals to du plus dw, right? We can write down dq as, and since dw is 0, dq is equals to du, and du is what? Internal energy. Yes, this plus 0. So dq is equals to du only. So what is the case? It means whatever heat you are supplying, this heat is used up only to enhance, to increase the internal energy of the gas. That means to enhance the speed, to enhance the kinetic energy of the gas molecules. This is the only use of the heat absorbed by the system. Or if the heat rejects some heat, in that case its internal energy will decrease. Okay? By the same way, so this is what the case of an isochloric process in which the volume is kept constant and whatever heat is supplied is used up totally for enhancement of its internal energy, and we can say dq, it can be calculated at NCV dt. The gas is taken from a temperature T1 to T2. This is the phenomenon, or it is very simple to calculate, evaluate the work done in that case. And PV diagram, indicator diagram of the process, is again very simple. P versus V. P versus V. Yes, P versus V graph. Volume is going to be constant. That means the indicator diagram kind of upwards, or it may be downwards vertically, where the system is taken from A to B, means the pressure is taken from P1 to P2, definitely the temperature here is T1, and finally the temperature becomes T2, but the volume, as you see, remains at V. So this process is this is the indicator diagram of an isochloric process. And yes, if they ask you volume versus temperature drop, since volume is kept constant, yes, here we can see volume is kept constant. So this is what the VT graph, volume versus temperature drop. And if I plot pressure versus temperature drop, yes, definitely it will be a straight line like this. Here you can see pressure is increasing as well as temperature also increasing here. So this is what P is directly for PV, since PV is equals to nRT, right? P is equals to nR upon VT. Since V is a constant, P is, we can check, P is directly proportional to T. In numericals, sometimes they don't give you the indicator diagram. Okay, this is the indicator diagram, and these are its corresponding graphs. Indicator diagram is this, or which is a graph P when P is plotted against V, but some other corresponding graphs are also given. From there, they may ask you several questions, or they may ask you in this way that which of the graph is correct. Some of the graphs options will be there, and out of this only one will be correct. So you have to be very careful while choosing this. This is what P versus theta. This is what in an isotropic process, and that is what the total procedure is. Okay, and so we have finished all the 4 processes. Okay, apart from this, let us have some other processes. The one more, okay, last but not the least, is the free expansion. One is the free expansion. There is a case of free expansion. What is free expansion? Or what do you mean by the term free expansion? How does it happen? Let us have a situation in which we have a container. There is a container, okay, completely insulated. That means insulated container. The real life examples of free expansion is exactly spreading of a perfume. Spreading of a perfume in the class, in the room. When you spray with the spray button, right, the atomizer, you get the spreads in the room. So this is an example of free expansion, like that. You still understand. When a container is totally insulated from the surroundings by insulating coating, and there is a boundary wall over here. Okay. Here gas is there. The gas is filled in one end and other end is kept empty. When this boundary wall is ruptured in any way, or an opening is allowed, right? What happens? The gas expands rapidly in the other chamber also. It rapidly enters, and since in this process no heat is allowed to enter, that means dQ is not allowed to enter nor allowed to leave it. So we can say what a free expansion is also, it rapidly fills the second chamber of the container. That means we can say free expansion is also a fast process, as well as since no heat is allowed to enter, since it is fast, so it doesn't get time to exchange its heat to the surroundings, or it doesn't get time to absorb heat from the surrounding. So it is what exactly fast and adiabatic. Since it is fast and adiabatic. Now second thing is that since here in this case the rate change in internal energy, since there is no work done, by the gas, we can say work done by the gas is 0. Since it is adiabatic, dQ is obviously 0, and since there is no mechanical work done, nothing is being pushed, no boundary wall is being pushed, okay, so dW is 0 only, and since dW is 0, dQ is 0, from the very first law we can write down du is 0. That means this free expansion takes place at a constant temperature. This is what the situation is. When it is done, this is the case of free expansion. In free expansion, we can conclude the discussion like this, that free expansion is a fast and adiabatic process in which the heat is neither allowed to enter nor allowed to escape out, and the work done by the system is 0, or the gas is 0. Since these two quantities are 0, from the first law of thermodynamics, we can say du is equals to 0. That means the free expansion takes place at a constant temperature. Okay. This is all about the first law. Now, since first law is so useful, it also explains a relationship between the work done and heat. It gives us a relation between heat and mechanical work. Yes, but the failure, limitation, you can say. The limitation of the first law is what lies over here only. We have just seen that it is not necessarily, it doesn't decide, it can't tell us that what are the conditions which allows heat to either enter a system or to leave a particular system. It means it remains silent over there. It doesn't tell you when the heat is absorbed or when heat is released. So it doesn't give you an idea of the direction of flow The second thing, I told you in the beginning that the first law depicts the relation between the amount of heat absorbed by a particular system and side by side what will be its mechanical advantage, or how can we use heat by supplying heat to system, how can we perform a mechanical work by the system. Right. Whereas second thing is also very important. Second limitation of this is also to be kept in mind that the first law fails to tells you a fraction of heat. It fails to tell you what fraction of heat will be converted into mechanical work, or will be useful to perform some mechanical work by the system. That means, yeah, it is relations. The only importance is that it gives you an equivalence. It decides or describes the equivalence of heat as well as mechanical work, but it fails to decide the direction of flow of heat, as well as it fails to decide that how much heat will be converted into mechanical work, as well as it remains silent if you ask it, sir, why not the total heat getting converted into mechanical work, whereas mechanical work can be completely converted into heat. That is very much easy, right? But the second one is not possible. That means flow is necessary. This process, you can say, is not symmetrical. Okay, so this is the situation, and these are the limitations. One more case, one can use it as cyclic process. A process is said to be cyclic means cycle. Cycle is from where you start, after moving here and there, after having a path trajectory. Yes, the particle reaches at the same point and starts again following the same trajectory. Such a process is known as such a motion cyclic motion. Similarly, there is a cyclic process in thermodynamics. What the cyclic process is? What does it mean? Suppose we have a pressure versus volume graph like this. Suppose a gas is taken from A to B like this. It is taken from A to B. Yes, when it is taken from A to B, definitely at A, there is a initial state of the gas is A, having the values of P1, pressure as P1, volume say V1, and temperature say T1. Whereas at B, it has the values of the variables as P2, V2 as well as right. So these three variables P, V and T, as you know, they are variables, thermodynamic variables, and they together decides the state of the gas, state of the thermodynamic system, and system is taken from the state A to state B according to the trajectory. Right. Whereas, you see, now the next part, when it is taken from B to A, and next part in the first part, the first process, the gas system was taken from A to B, right? A to B according to this path, and yes, this process is not reversible. Don't mix with the reversible one. A reversible process is what? A process is said to be reversible. Say you have a point, initial position over here, and the final one is here, say at B. So graph process is taken from A to B and later from B to. So when A to B, this is process number 1. When B to A, let me call it process number 2. This process over here, since they are passing this to the same trajectory, is followed. The path is followed. Similarly, right? In the same way, we can call it. This is a graph of a reversible process. But this one is not reversible. Whereas the initial and final, right? Initial state is B, final state is B, and again we start from B and reach at A. So at the end of the complete process, right? We are attaining the same value of the variables. That means the gas is coming back to its initial state. This is what a cyclic process. This is what a cyclic process. So in the cyclic process, obviously, you know, I'm just showing you like this. See, the first case, this is the area area under the pressure PV graph gives you the work done, as you know, right? So this result, volume is expanding, initial volume is less, V1, final volume is V2, the gas is under expansion. Definitely there is a positive work done taking place in this case. But whereas when the process 2, when you are coming from B to A, yes, volume is decreasing, gas is under compression. Since the gas is under compression, one can say in the first case W1 is positive and W2 is negative, right? But since positive work done is more, in that particular scenario, positive work done is more, whereas negative work done is less. We can say what? The net work done, W net, is positive. Let us see another case. Let us see another case. A gas is taken from A to B, B to C, C to D, and finally it brought back at A. Say pressure at A is P1, pressure at B and C both is P2, volume at A as well as D is V1, volume at C and D is V. Now in this process, this is cyclic one, because the gas is starting from the system, the operations are started from one and through different 4 thermodynamic processes, right? First one, as you can see easily, here pressure is constant. So the first process is process number 1 is what kind of process? Isobaric process, right? Pressure is kept constant. In the second part, in the second graph, when you are going from B to C, what we are keeping constant? We are keeping the volume constant. So here we can say what? This is what? An isobaric process. Third case is also performed at constant pressure, but this time the value is a bit more, okay? And again pressure but P2, and this P2 is kept constant. So second one, CD, is also an isobaric process, and as DA is an isobaric process. So there are two isobaric processes involved in this cyclic process, right? And from the starting point A, the initial state, you can say P1, V1, T1, right? And the final process, at the end of the cycle, we are reaching at A. That means the system is attaining the initial value of its thermodynamic variables at the end of the process. So this is again a cyclic process, but this time let us calculate the work done in the first process. As it's going from like this, this is what? This work done is say W1, this work done is 0, this work done is minus W2. So it is what? Since my W2 is negative and more, we can say net work done will be negative. So what conclusion we can write down? We can write down in our short notes that in the cyclic process, if the cycle is clockwise, when the cycle is clockwise, work done is positive. When the cycle is anti-clockwise, counterclockwise, the cycle work done becomes negative. Now check about internal energy. Check about the change in internal energy during the whole process, during the complete cycle. Since you can see that after cycle, the volume temperature comes to be at the same value. That means the value of the variable T regains itself. That means there is no change in the temperature of the system, or since we know du is equals to n Cv dt, dt is 0, du is j. So in the cyclic process, one thing is when you conclude work done is positive, work done by the gas is positive, dW is positive. So for a positive work done, and heat is also absorbed by the system. Heat is Q is absorbed. Yes. And when the work done is negative, heat is rejected. They will ask you questions like this: how much the amount of heat either absorbed or rejected by the system. So we have to take care whenever the cycling process are given and the cycles are clockwise. Yes, since work done is positive, the positive work done, right? The heat will get absorbed in the system, and when 0 or change in internal energy is always 0. Okay. Now, just for your understanding, let us have a question. I am giving you a question just for a quick review so that you can understand it properly. Say, this is the PP diagram, okay, origin, and there are three processes. One, this, second one is this, and third one is this. Okay, there are three processes mentioned over here. This one is process number 1. This is a process, another one process. Process number 1. This is the process number 2. This is thermal process 3. Okay, and the values of the variables are as usual. Here is P1, V1, and T. Here the value of the variables, right? So value of P1, V1, and T1. Similarly, at the point P, the value of the variables P2, V2, and T. There are three cyclic definite processes. The system is taken from one end to another. Now the question is not this. They will ask you find the amount of heat. Find the amount of heat absorbed by the system in, or let us the heat absorbed by the system by the three processes. In first process, and the heat is Q1, the second one Q2, and third one Q3. So Q1, Q2, Q3 be the amount of heat absorbed in three different processes. Then the ratio Q1 is to Q2 is to Q3. How to solve this question? What is the ratio? There will be 4 options given. How to solve this question now? Can you think about it? Yes. What is the similarity? Similarity is that all the three processes have the same origin. That means they are originating from A. They are initiated from A and they are finished at B. Okay. The trajectories are different, but the initial and final states are similar. Since we know well, internal energy U is a state function. U is called a state function. U is not a path function, so it doesn't depend on the path. It depends only on the initial and final states of the gas, and initial and final states of all three gas processes, right, is similar. That means U1 is equals to U2 is equals to U3. And right, work done. You know well, work done is what? Amount of work done is the area between the PV graph and the volumetric axis. So maximum work done is in the first case, or you can say Q1 W1 in the process. Suppose work done is W1. Second process W2. In third process it is W3. And one can easily say W1 is greater than W2 and W2 is greater than W3. Now come to the alignment of first law. Yes, this question will be solved according to the first law, and which says what? That dq is equals to du plus dw. Right? So W1 plus W is greater than W2 and W3, and U1 is that. So what we can say? Q1 will be U1 plus W1, Q2 U1 U2 plus W2, and Q3 is equals to U3 plus W3. Yes. Okay, which one is maximum? W3 is minimum, W1 is maximum, U1, U2 are equal, so that doesn't make any sense. And finally, Q1 will be the maximum one, or Q1, right, will be greater. Q1 is greater than Q2, Q2 is greater than